Now, we've laid a firm foundation in probability and distribution theory, and we've used that to study sampling distributions, which is the link between descriptive statistics and inferential statistics. In this lecture video, we're going to start looking at the basic concepts of statistical inference. Now, from here on out, for the rest of the course, we're going to be looking at different methods involving or ways of performing statistical inference. Now, there are two main categories of procedures within statistical inference. The first would be hypothesis testing, procedures for making decisions between competing assertions about population parameters of interest. And then the second would be estimation, procedures for coming up with what we might call a data-based guess as to the true value of the population parameters of interest. Now, there are two kinds of estimates. The first would be a point estimate. The process of point estimation gives us a single value based on the data. The second type would be confidence interval estimation or confidence interval estimates. The process of confidence interval estimation gives us not a single value, but a range of plausible values that the population parameter could possibly take on. Now, the overall idea behind hypothesis testing is the following. We formulate opposing statements about the population of interest. These statements will be called the null and alternative hypotheses. We then obtain a sample from the population, and we study the sample using the descriptive statistics that we have looked at up to this point. For example, we might calculate one or more measures of location, such as a sample mean, a sample median, and so forth. We might calculate one or more measures of variation or dispersion, such as the sample variance, the sample standard deviation, and so forth. So we study the sample, and then we want to extrapolate that or generalize that to the population. Now, if the observed data are inconsistent enough with the null hypothesis, then we may choose to conclude that the null hypothesis is false and that the alternative hypothesis is true. Now, the question is, how inconsistent does the sample data have to be with our preconceived notions, our assumptions, which are contained in the null hypothesis, in order to lead us to reject that null hypothesis? We'll talk about that briefly in a while. Now, the components of a hypothesis test consist of the hypotheses, a test statistic, which is kind of a dipstick or a barometer that we use to measure reality, a rule for evaluating the observed value of the test statistic, sample data from which the test statistic will be calculated, and then the conclusion or conclusions regarding the hypotheses. Now, a hypothesis test consists of a set of hypotheses stated in terms of one or more population parameters of interest. There are two hypotheses. We will call them the null hypothesis and the alternative hypothesis. And they are set up in such a way, they're stated in such a way that they are opposing statements. They are opposites or logical complements of each other. So in setting them up that way, exactly one of those statements is going to be true. Now, the null hypothesis is denoted H sub 0 or H naught, and it's a statement about one or more population parameters that usually represents the status quo. The treatment or intervention has no effect, or there is no difference between populations if we are comparing populations. The alternative hypothesis, denoted usually by H sub 1, but sometimes by H sub A, is a statement about one or more population parameters that usually represents what the researcher would like to prove. The treatment or intervention does have an effect, or that the populations being compared are in fact different. Now, we always have to keep in mind that the alternative hypothesis will always be the opposite of the null hypothesis. Then we have the test statistic. This is a value computed from a sample that is used in the decision-making process. It's a random variable because it's computed from the random sample, and it therefore varies from one sample to the next. And so in order to use a test statistic to decide between two competing assertions contained in the null and alternative hypotheses, we have to understand how that test statistic behaves. We have to know something about its sampling distribution. Then we have the rejection or the critical region. Now these are the values of the test statistic for which we will conclude that the null hypothesis is false. In other words, for which we will reject the null hypothesis. Now, to determine the rejection region, like I was saying, we need to know how the test statistic behaves when the null hypothesis is true. In other words, we need to understand and know something about the sampling distribution of the test statistic under the conditions of the null hypothesis. Okay, then we need sample data. Now, depending upon the experiment, that data can be obtained in one of several ways. For example, if it's a sampling experiment, then we will need random samples from one or more populations. If it's a designed experiment, we'll need to randomly assign treatments to experimental units and then conduct the experiment, measuring one or more response variables to be used in the analysis. In either case, notice that we have the word random. Random sampling, if it's a sampling experiment, random assignment of treatments to experimental units, or vice versa, random assignment of experimental units to the treatments, however you want to think about that. But in each case, we have some sort of random process or randomization involved in and intentionally injected into the experiment. Now, why do we do this? Well, randomization provides the probabilistic framework that required by the statistical tests. And it's that probabilistic framework which gives a validity to the statistical test itself. Now, there are a variety of ways of sampling from populations. In fact, you could take a whole semester course on different random sampling techniques. For example, simple random sampling, systematic random sampling, stratified random sampling, cluster random sampling, two-stage cluster random sampling, all sorts of different kinds of random sampling techniques. Likewise, for designed experiments, there are a wide variety of ways that experiments can be conducted in terms of randomizing treatments to experimental units and performing the experiment. And so because there are so many different ways of performing experiments, it stands to reason that the specifics of the sampling procedure or the randomization process will in fact affect the probabilistic framework, which is what gives the inference procedure, the hypothesis test, its validity, and also eliminates researcher bias. And because of this, in order to do a proper, valid analysis, we must take into account this probabilistic framework in the analysis in order to obtain valid results. So, in other words, we have to know how, if it's a sampling experiment, we have to know how the populations were sampled. If it's a designed experiment, we have to know the process by which treatments were randomly assigned to experimental units. And we have to take that into account when we do the analysis. That type of information will determine the appropriate form of statistical model that we use for the analysis. Now, if we use the wrong model, for example, if we don't take into account the type of sampling process or the type of process used to randomly assign treatments to experimental units, then we will not have a valid analysis and the results cannot be trusted. So it's extremely important that we understand how an experiment was conducted, whether it's a sampling experiment or a designed experiment, in order to properly analyze the data and get valid results. And then we have the conclusions regarding the hypotheses. And for the purposes of this class, I will typically ask you to state the hypotheses in a couple different ways. The first, I'll ask you to state the hypotheses in statistical terms, in terms of the parameter or parameters that are being tested. And then also, if there is a context to the class, or to the example, to the problem, if there's a context, if there's a real world situation associated with the problem, then I'll ask you to translate the conclusions that were stated in statistical terms into the language of the original problem. Now, here are the steps involved in a hypothesis test, and if you look at different books, different resources, they may list the steps slightly differently, but this is the set of procedures or the steps that I use. So the first is to state the null and alternative hypotheses, then determine the test statistic to use and write out its formula. Once we do that and we know the test statistic we're going to be using, we need to determine the rejection region and write out the rejection rule. Now, these first three steps we can think of as writing out or coming up with a protocol for the experiment. We don't actually have to have any data to do these things. What we're doing is setting up our decision-making process. We're setting up with the first statement here, the first step. We're defining the problem to be solved, essentially, and stating that problem in terms of one or more population parameters in our hypotheses. And then we're setting up the procedure by which we're going to draw conclusions once we get the data. Now, to go beyond this third step, we have to actually collect data. So that's the fourth step. We collect the sample data and calculate the test statistics. So in other words, we perform the experiment, whether it is sampling populations or performing the design experiment. We have to do that and then measure the data, collect the data that we'll use. And then once we have that data, then we calculate the value of the test statistic. Then we evaluate the test statistic by looking at the rejection criteria to see if the rejection criteria have been met. Okay, so we draw conclusions based on the observed value of the test statistic and the rejection rule that was determined in step 3. And then finally, we state our conclusions both in statistical terms and in the language of the original problem when there is a context to the problem. Now, there are 4 possible scenarios when drawing conclusions about hypotheses. For case 1, or in case 1, the true state of nature is that the null hypothesis is true, and then the conclusion based on the data is that we conclude that the null hypothesis is true. And so when that's the case, we've come to the correct conclusion. The second scenario, case 2, the true state of nature is that the null hypothesis is true, but based on the data we obtain, we conclude that the null hypothesis is false. Now, when this happens, we have come to an incorrect conclusion because we've rejected a true null hypothesis. This kind of inferential error is called a type 1 error. The third possibility, case 3, is that the true state of nature is that the null hypothesis is false, but based on the data that we obtain, we conclude that the null hypothesis is true. So again, in this situation, we've come to the incorrect conclusion because we have failed to reject a false null hypothesis. Now, this type of inferential error is called a type 2 error. And then finally, the fourth possibility, the true state of nature is that the null hypothesis is false, and based on the data that we obtain, we conclude that the null hypothesis is false. So when that happens, we have come to the correct conclusion. Now, I've got a diagram that I've made that I think will help us visualize this perhaps a little bit better. And so I have a two-way table. The columns, well, number one, this is the possible decision-making outcomes when performing hypothesis tests. And so the columns here correspond to the true state of the null hypothesis. Either the null hypothesis is true or the null hypothesis is false. These two rows correspond to our decision about the null hypothesis based on the data. All right, and so we can conclude that the null hypothesis is true, or we could conclude that the null hypothesis is false. Now, if the null hypothesis is in fact true, and based on the data we conclude that it's true, then obviously we've made a correct conclusion. If the null hypothesis is false, and we conclude that it's false, again based on the data, then again we have drawn the right decision or right conclusion. We've made the correct decision. On the other hand, if the null hypothesis is true, but based on the data we conclude that it's false, then we've committed a type 1 error. We've come to the wrong conclusion. We've rejected a true null hypothesis, and that again is called a type 1 error. And then finally, if the null hypothesis is false and so therefore should be rejected, but based on the data we conclude that it's true, then we've again come to the wrong conclusion because we failed to reject a false null hypothesis, and that is called a type 2 error. Now, in any real-world hypothesis testing situation, it's always possible that we will commit either a type 1 error or a type 2 error. If the null hypothesis is true, for example, and by the way, we would never know whether or not the null hypothesis is true. If we did know that, we wouldn't have to do statistics. We wouldn't have to do hypothesis testing. But in those situations where the null hypothesis happens to be true, there's always going to be a positive probability that we commit a type 1 error. And in those situations where the null hypothesis is in fact false, there's always the possibility that we'll get a hold of a data set for which we will conclude that the null hypothesis is true, and therefore we would be committing a type 2 error. So ideally, the probability of a type 1 error and the probability of a type 2 error would always be 0, but that's never going to be the case. There's always a positive probability of either one of these types of errors. And so it is useful to, when thinking about hypothesis tests and when designing hypothesis tests, it's useful to assign notation or define notation corresponding to these different kinds of errors. And then we can use those concepts and that notation in helping to set up our hypothesis test. So we let alpha denote the probability, the conditional probability, by the way, that we get a hold of a data set that leads us to conclude that the null hypothesis is false, when in fact the null hypothesis is true. Okay, do you see that? Alpha is the conditional probability of concluding that the null hypothesis is false when in fact it's true. So alpha is the probability of a type 1 error. Beta, on the other hand, is the conditional probability of concluding that the null hypothesis is true when in fact the null hypothesis is false. So beta is the probability of a type 2 error. So with that notation, like I was saying, for any realistic real-world problem, alpha and beta will always both be positive. They won't be 0, not in a realistic real-world problem. Now, this alpha, the probability of a type 1 error, is also called the significance level of the test. And it's something that we have control over. We have direct control over the significance level of the test. As we'll see, we actually choose the significance level we want to use for the test. So we will set up our test so that alpha is at a predetermined level. Now, we don't have direct control over beta. Beta depends on several things. It depends on it does depend on the significance level. It also depends on the true value of the parameter about which we're testing a hypothesis. It depends on the sample size. It depends on the variability that exists in the population. There are a large number of things that the beta depends upon. Beta is actually not a single value. If we were to represent this correct, technically correct mathematically, which we will do a little bit later, we would see that beta is actually a function of all those characteristics and perhaps even more than what I just listed. Now, we want to think about the probabilities of type 1 and type 2 errors. We want to think about alpha and beta, and in particular, what we're looking at right now is we're thinking about the relationship between alpha and beta. Like I was saying on the previous slide, one of the things that beta depends upon is the significance level alpha. And so for a fixed sample size, alpha and beta are inversely related. In other words, if we decrease the alpha that we're going to use for a test, we necessarily increase beta. And if beta decreases, then alpha increases. We could also say here that if we increase alpha, then beta will decrease. So that is the relationship in general between alpha and beta. Now there's also a characteristic of a hypothesis test called the power. Power is the probability of correctly rejecting the null hypothesis. In other words, concluding it's false when in fact it is false. So power is a conditional probability, just like alpha and beta were conditional probabilities. And stated as a conditional probability, power is the conditional probability that we will get a hold of a sample that causes us to reject the null hypothesis when in fact the null hypothesis is false and therefore should be rejected. Now by the complement rule, this is equal to 1 minus the probability that the null hypothesis is not rejected when in fact the null hypothesis is false. In other words, it's equal to 1 minus beta. So power and beta are related in this way. They are inversely related as well. They sum to 1. Power is equal to 1 minus beta, or equivalently, beta is equal to 1 minus power. Now ideally, we would like both alpha and beta to be 0, and therefore the power to be 1. But in any real testing situation, alpha is going to be greater than 0, beta is going to be greater than 0. In other words, there's always going to be a positive probability of either committing a type 1 error or committing a type 2 error, and therefore power will be less than 1. Now, if possible, even though both alpha and beta will be greater than 0, if we could somehow manage it, we would like both alpha and beta to be small, in other words, close to 0, and power to be big or close to 1. But for a fixed sample size, this may not be possible. To make both alpha and beta small, we may need to increase the sample size. Remember that alpha and beta are inversely related. If we decrease alpha, if we make it closer to 0, then for a fixed sample size, beta will necessarily increase. And so we can't make both of them small when we make alpha small and we have a fixed sample size. In order to make both alpha and beta small, we must increase the sample size. And one way to think about that is we have to get more information about the population from the population. We have to get a bigger sample size, which is getting more information about that population. Now, when we first started talking about hypothesis testing, we talked about the big idea or the overall idea of hypothesis testing. And we said that what we do is we state or come up with competing statements about the population of interest, the null and alternative hypotheses. We collect a sample from the population of interest, and then we look to see whether or not the data are consistent with the null hypothesis. If the data are consistent with the null hypothesis, then we really have no reason to reject the null hypothesis. But if the data are inconsistent with the null hypothesis, then if the inconsistency is great enough, that should lead us to, at some point, reject the null hypothesis. And so that's what we're looking at here. How to quantify assessing the consistency or inconsistency, however you want to look at it, between the null hypothesis and the observed data. Now, to do this, we use what is called the p-value. The p-value is a measure of how likely the observed results are if the conditions of the null hypothesis are true. More technically, it is the conditional probability. There we go, we have another conditional probability. I think you're probably starting to see why we study probability so much. We use these different kinds of probabilities all throughout hypothesis testing. So the p-value of a test is the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed if the null hypothesis were true. Now, when we say at least as extreme, what we're talking about, what that means is in the direction of the alternative hypothesis. Now, we'll see what this translates into in particular situations, but this is the general definition of a p-value, and this is fairly explicitly stated, and so this is in general how we would state it. We will translate this into particulars when we get to particular situations. Now, one thing I want to emphasize is that a p-value is not, I repeat, it is not the conditional probability that the null hypothesis is true given the data. So let me show you another slide here that will hopefully emphasize the difference between these two types of probabilities. Both of these are conditional probabilities, but they're not the same. So this is a set of slides that I used in another class, but I think it's helpful to see it here. And so we want to differentiate between the p-value and the conditional probability that the null hypothesis is true given the value of the test statistic. And so to do this, I'm defining the following notation and the following events. So I'm going to let H like this, denote the event that the null hypothesis is true. And I'll use the notation H1 to denote the event that the alternative hypothesis is true. Okay? And then I'll use the abbreviation TS to denote the event that that we observe a value of the test statistic that is at least as extreme in the direction of the alternative hypothesis as that which has been observed in the data. So these three events are defined in that way. And so using this notation, then the p-value is defined to be the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed in the data if or given the null hypothesis is true. On the other hand, this notation, this conditional probability is the conditional probability that the null hypothesis is true given a observed value of the test statistic. And so you can see that these two conditional probabilities are not the same. In this first one, we're conditioning on the null hypothesis being true. In the second one, we're conditioning on observing a value of the test statistic at least as extreme as that which has been observed, and so forth. So, and also, in the first conditional probability, the event of interest is TS, whereas in the second conditional probability, the event of interest whose conditional probability we want is the probability that the null hypothesis is true. So you can see here that these two probabilities are not the same. So the p-value is not the conditional probability that the null hypothesis is true given the value of the test statistic. Now we might ask the question, what is the relationship between this conditional probability here and the p-value? Are they related? And if so, what is the nature of that relationship? Well, we're not going to get into that right now. It's an interesting question, and but for right now, we just need to understand what the definition of the p-value truly is, and we don't want to mistake, or we don't want to mischaracterize the p-value by saying that it's this thing down here. It's not the case. Now, how do we use the p-value? We use the p-value to draw conclusions. And how do we do that? Well, we reject the null hypothesis in favor of the alternative. In other words, we reject the null hypothesis and conclude that the null hypothesis is true if the p-value is less than or equal to alpha. Remember, alpha is the significance level of the test that we have chosen to use. Now, this approach is equivalent to the approach using a test statistic in the rejection region. In other words, and in fact, it's equivalent to rejecting the null hypothesis if the test statistic falls in the rejection region. Now, the main reason that we use p-values in drawing conclusions about a hypothesis test is that allows different readers of a study to reach their own conclusions, possibly different conclusions, by using different significance levels. So, for example, suppose somebody demands a lot of evidence in order to reject the null hypothesis. Well, that person will use a smaller significance level, a smaller alpha, than somebody who doesn't require as much evidence to reject that null hypothesis. And so, in this way, different readers of a research study will be able to draw their own conclusions based on the level of evidence that they deem necessary or that they deem appropriate for, or in order to reject that null hypothesis. So this is an overview of what hypothesis testing is, the components that make up a hypothesis test, the steps involved in a hypothesis test, and various values or characteristics of a hypothesis test, like the significance level, beta, the probability of a type 2 error, the power of the test, and so forth.